Hi. Yeah, so this is joint work with Virginia Vasilevska-Williams, and today I'm going to tell you about matrix multiplication. So this is just the algorithmic problem. You're given two n by n matrices x and y, and you want to compute their product z. So you can think of these as matrices over any field you want, and let's say we're working in a computational model where field operations take constant time. So we're like measuring how many field operations do you need to multiply two matrices. So the most straightforward algorithm where you just like use the definition of matrix multiplication uses n cubed time. But you probably know there was this great breakthrough algorithm by Strawson where he improved it to n to the 2.81 time. And then since then there's been lots and lots of work on this problem, leading up to the best known runtime was n to the 2.372 something. So people usually call this exponent omega. So you say matrix multiplication can be done in n to the omega time about, and the best known bound right now on omega is 2.372864, okay. But the big open question is whether or not omega equals 2. I think a lot of people believe omega equals 2, but it's a big open question whether it is and how we can get there. So let me give you a one-slide, really high-level overview of how matrix multiplication algorithms that we know work. And actually, most of the rest of my talk is going to be like saying this again in more detail. So the known approaches to matrix multi algorithms have two components. So the first is an identity, where you show that some trilinear form, which I'll call tensor, is efficiently computable. So what do I mean by that? Well, matrix multiplication is a trilinear form in that you get these two input matrices x and y, and then each entry of the output matrix is a bilinear form in the x entries and the y entries. So more generally, you could think of like a problem where you get two input matrices and you want each z entry to be just any bilinear form in the input matrices, and that's what I mean by a trilinear form in general. So the first step is an identity showing that one of these like variants on matrix multiplication is efficiently computable. And the second is a method which shows how to embed matrix multiplication into this other trilinear form that you showed was easy. And then these together give a matrix multi algorithm. You embed the matrix multi problem into this other thing. You solve that efficiently, and so you've solved matrix multi efficiently. So there are two main sort of approaches to designing these types of algorithms. The first is the Strawson and Coppersmith-Winograd approach, where the method is something that Strawson called the laser method. And while all methods work better on certain types of tensors than others, the laser method works really well on tensors with have certain structures, and like the best example of this is the so-called Coppersmith-Winograd tensor. This is actually a family of tensors. Like for each positive integer q, there's a Coppersmith-Winograd tensor. And actually all the record-holding algorithms since the 90s have used the laser method applied to the Coppersmith-Winograd tensor. But there's another maybe competing approach defined by Cohn and Oomans. That's the group theoretic approach, where here you use this group theoretic method that works well on tensors that are defined from groups in some way. The details are not so important, but there's sort of these two main approaches to designing these algorithms. So here they are again. So I'm now going to give you, I guess simultaneously, a summary of my talk and a summary of our results. So in the first part of the talk, I'm going to tell you about these methods for analyzing tensors. So here are the laser method and the group theoretic method. And I'm going to define three very general methods that subsume these for analyzing tensors. And sort of analogous to the name laser method, we're going to call them the solar method, galactic method, and universal method. And what I want to emphasize about these is that these are very general techniques which we don't know how to optimally use. So if you're not familiar with this stuff, the way to think about it is, so when you have a tensor and you're trying to use it to design a matrix multi algorithm, there's like a big search space of potential ways to use this to design an algorithm. And this search space is big, and it's really hard to find the optimum points in this search space. So these different methods are focusing in on smaller parts of the search space where it's easier to analyze and find optimal points. So like the laser method and group theoretic method are finding smaller places where it's easier to analyze, and then the solar method and so on are bigger and bigger supersets of these parts of the search space. But even though these are subsets of the search space, we still don't actually know how to optimally analyze these either. That's how you should think about them. And then in the second part, I'm going to tell you about limitations of these general methods we don't even know how to use. So there are some known limitations already. It's already known that you can't get omega equals 2 by using the laser method applied to Coppersmith-Winograd tensors. And similarly, there's a nice recent line of work showing you can't get omega equals 2 using like fixed groups and the group theoretic method. But these results, I think they leave a bit to be desired. Basically, like if you start with the Ambinus Filmus Legal result and you change the Coppersmith to integrate tensor a little bit, or you change the laser method a little bit, suddenly their lower bound result just doesn't apply anymore. So what we prove is a much more general lower limitation result. We show that the galactic method, this superset of superset method, applied to Coppersmith-Winograd tensors or fixed group tensors, or actually lots of other tensors like these too, I'll tell you more about them later, you can't use these tensors with the galactic method to prove omega equals 2. So if you want to prove omega equals 2, you either have to look at tensors like very, very different from the ones that we've been using, or else use a very different method that doesn't fit within this more general galactic method. So that's our main result. Okay, so now I'll try to be a bit more precise about all the things that I just said. So let's start with tensors. So the mathematical objects that we're going to be interested in today are called tensors. So throughout this talk, x, y, and z are going to be sets of formal variables. And you can think of these as like entries of the x, y, and z matrices. And a tensor is just a trilinear form or a trilinear polynomial in these x, y, and z variables. It's just for each triple of an x, y, and z variable, there's a coefficient in front of it. You can think of these as complex numbers. And we're going to be really interested in ranks of tensors. So you say a tensor has rank 1 if you can write the tensor as a linear combination of x variables times a linear combination of y's times a linear combination of z's. And this is actually the same as matrix rank. Like you say a matrix has rank 1 if it's the outer product of 2 vectors, and a tensor has rank 1 if it's the outer product of 3 vectors. And similarly, just like with matrices, the rank of a tensor is the minimum number of rank 1 tensors whose sum is the tensor you want. So that's a tensor rank. And the specific tensor we're going to care about is the matrix multiplication tensor, which is defined like this. For any positive integer m, it's this nice, really symmetric-looking tensor. So why do we care about this tensor? Well, this tensor has the nice property that it's kind of like a generating polynomial for matrix multiplication. And what I mean by that is, if you look at these two matrices of the x and y variables and compute their matrix product, then the result in the ik entry is exactly the coefficient of zik in the matrix multiplication tensor. So the coefficients of the z variables is what should be there in terms of the x's and y's. So if you get a rank bound on these matrix mult tensors, it leads to a really nice recursive algorithm for matrix multiplication. And if you've seen Strawson's algorithm before, it's basically the same idea. So if you show that the m by m tensor has rank k, then what you do is you block your input and output matrices into m by m block matrices. And then the rank expression, if you think about it, shows how to compute k different products of like a linear combination of the x blocks times a linear combination of the y blocks, so that every z block is a linear combination of those. If you think about it for a second, it's not too complicated. And so this gives a nice recursive algorithm where to multiply n by n matrices, you do k multiplications of n over m by n over m matrices, plus order n squared time to do all these linear combinations, which leads to a runtime of n to the log base m of k. So there's the same thing I said. If you show it as rank at most k, then the n by n matrix multiplication can be done in time n to the log base m of k. So omega is usually defined as the minimum or the lim inf over all m of the log base m of the rank of the m by m tensor. So I just showed you that we can get a matrix mult algorithm whose runtime is about n to the omega. There's like a little 1 because of the lim infs and all this stuff. But you might be thinking, oh, but couldn't you come up with some completely different type of matrix mult algorithm? Actually, in certain models of computation, like if you want an arithmetic circuit for matrix multiplication, you can assume without loss of generality that your algorithm has to be of this recursive form, up to some losing just constant factors. So assuming you want an arithmetic circuit, you can actually just define omega in this way, and it's the same as the runtime for matrix mult. Okay. So the goal is to give rank upper bounds for matrix mult tensors. So for instance, Strawson showed that the 2 by 2 by 2 tensor has rank at most 7. And you've probably seen this rank expression before. It looks like this. Okay. Later, Pon showed that the 70 by 70 by 70 tensor has rank at most 143,000 something. I'm not going to show you what that one looks like. But these things get really unwieldy really quickly. So actually the approach people take is to go through different starting tensors instead of starting directly with the matrix mult tensors. So the approach looks like this. You start with a different tensor T, and you show that T has small rank instead of the matrix mult tensor has small rank, and show that T, or a tensor power of T, if you haven't seen tensor power before, it doesn't matter too much. It's like a polynomial power, basically, when you think of it as a polynomial. You show that like a power of T contains a big matrix mult tensor. And what we want is that if we define contains in the right way, then this will mean that if A contains B, then the rank of A gives an upper bound on the rank of B. And so this method will give upper bounds on the ranks of matrix mult tensors and give upper bounds on omega like we want. So I'm going to tell you about 3 options of like increasing strength of what contains means. And these are going to correspond to the solar and galactic and universal methods I mentioned before. So the first is called zeroing out. I'll leave in the corner the property that we want to make sure this has at the end. So I'll denote it with this like triangle sub ZO thing, zeroing out from A to B. And this is just, you get from A to B by removing all occurrences of some of the variables in A, like setting those variables to 0. It's very simple. Let me give an example. So if A is this, whatever tensor, and B is this, which is the first 2 terms of A, then you can get from A to B by setting y1 to 0. So here are the places in A that y1 appears, and when you set them to 0, those 2 terms go away and you're left with B. So that's a zeroing out from A to B. So let me make 2 notes about this. First of all, you can't zero out from a tensor to any subset of its terms. So for instance, if you look at this tensor C here, that's the first 3 terms of A, there's no zeroing out from A to C. And the reason is the term that we want to get rid of from A, the x1, y1, z1, it shares each of its variables with terms in C that we want to keep. So we can't set any of them to 0, so there's no way to just get rid of that one term. Okay, so we can't get to anything. But it's not so hard to see that if there's a zeroing out from A to B, then the rank of A is greater than or equal to the rank of B. You basically just do that same zeroing out to the rank expression also. So we have that property in the corner that we want. Okay, so that's zeroing out. The next more general one is called monomial degeneration. I'll denote it with this sub-MD triangle. So the definition is more complicated, so bear with me for a second. So here, what you want to do is show there's a sequence of tensors so that each one is gotten from your original tensor A by multiplying by coefficients. Before it had to be zeros, but now it can be any coefficients. And such that the tensor C you're going to is the limit of this sequence of tensors. Okay, so let me give an example again. That'll make it much more clear. So here's the same tensors A and C from the last slide. What we're going to do is, for every epsilon bigger than 0, we're going to multiply y1 and z1 by epsilon and x1 by 1 over epsilon. So what happens when you do this? Well, in the first 3 terms of A, the epsilons and 1 over epsilons cancel out with each other. But in the last term of A, there's going to be 1 more epsilon than 1 over epsilon, so we'll get this thing at the end with a coefficient of epsilon. And then if you look at just the sequence of these tensors, as epsilon goes to 0, the last term goes to 0, so the last term goes away, and it converges to C. So this gives a monomial degeneration from A to C. So it's not hard to see if there's a zeroing out from A to C, then there's also a monomial degeneration, so it's at least as strong. And this specific example of A and C show that it's actually strictly stronger to do monomial degenerations instead of zeroing outs. Showing that it has the property in the corner is not trivial at all. I'm not really going to say much about it, but there's a really nice paper by Binney where he shows if you take tensor powers and do some nice things involving the term border rank, then it all works out nicely and you still get the property that you want. Okay. And then there's an even more general thing called arbitrary degeneration, or just degeneration. I'm actually not even going to tell you about this today because I don't have time, but I just want you to know there's even more crazy stuff with coefficients and limits and linear combinations and all these things. Okay. So to summarize, the known approaches to matrix multiplication, you choose a tensor T, you show that its rank is small, and you find a degeneration to a matrix mult tensor. And depending on what type of degeneration you're finding, zeroing out corresponds to the solar method, monomial degeneration corresponds to the galactic method, and this crazy arbitrary degeneration corresponds to the universal method. So, what tensors have actually been used in this method? Like, where are the tensors coming from? So Strawson's algorithm can actually be seen as using the 2 by 2 by 2 matrix mult tensor itself, and sort of then the degeneration's like the trivial one, and the hard part was just showing the rank upper bound for it. One of the first algorithms that used a tensor that's not a matrix mult tensor was Strawson's in '86, where he used this so-called Strawson tensor that it doesn't matter at all what this is, but it's something which is not a matrix mult tensor. And up to the most recent results use this so-called Coppersmith-Winograd tensor that, again, it doesn't matter what this is right now. I'll tell you a little bit more about it in a second, but it's something which is not a matrix mult tensor. But one thing that's really interesting is all these approaches that we know actually just use zeroing outs, or the Solar method, to find the embedding of matrix mult into your tensor. So in other words, the picture really does look like this, that the laser method and the group theoretic method are just certain ways to find zeroing outs, and they might not even be the best ways to find zeroing outs. So with this in mind, I can more precisely say what our limitation results are. So again, these two approaches, they focus on particular nice tensors, like the laser method works on tensors with some structure, like the Coppersmith-Winograd tensors. The group theoretic method works well with these group tensors. And they both give ways to show that there's a zeroing out of your tensor into a big matrix mult tensor. But not only is it possible that there's better zeroing outs, in fact, I think it's quite likely there are better zeroing outs. Like, you can view the improvements from Coppersmith-Winograd's original paper to the best known bound now as like slightly improving the laser method to get better bounds out of the Coppersmith-Winograd tensor. So most likely there are better zeroing outs, not to mention you might be able to use monomial degenerations to do something even better. But what we show, our first main result, is that there's a universal constant bigger than 2, such that you can't get a better bound than omega using that constant, than that constant, using the galactic method applied to the Coppersmith-Winograd tensor for any Q. And in fact, our proof works for like a big generalization of the Coppersmith-Winograd tensors too. I'll tell you a little bit about that in a second. Yeah, we'll see. It only uses like a tiny bit of the structure of the tensor. So actually, it can apply to a lot of other things. And yeah, after this slide, I'll give you like a sketch of the proof of this theorem. We also prove a similar type of thing about group tensors. Like for any fixed group, there's a constant bigger than 2 such that you can't beat that constant using the group tensor and the galactic method. Yeah, I don't really have time to tell you much about this. I want to tell you 2 quick notes though. The first, that theorem 2 actually doesn't completely rule out using group tensors to get omega equals 2, because it's a different constant for each group. So you could like try to find a crazy sequence of groups where these constants converge to 2 and possibly still use this type of approach. Another note is that, well, after we wrote our paper, we found this other paper by Sawin who actually proved the same type thing about group tensors. So actually group tensors have been, this type of general limitation was known about them before. Okay. So let me, in my last few minutes, tell you a little bit about the proof for the Coppersmith-Winograd tensor, like the tensor that was used to get all these bounds. Let me tell you how we prove our limitation about it. And the idea is to use something called independent tensors. So a tensor is an independent tensor if no 2 of its terms share any variables at all. And I'll denote it with this like triangle bracket Q notation. So we're going to be interested in monomial degenerations to independent tensors. So for tensor B, I'll write I of B as the biggest number of independent terms you can monomial degenerate B into. And more generally, if you're using tensor powers, you can use I tilde of B as like the tensor power version of I of B. So this is how many independent terms you can monomial degenerate your tensor into. And one really simple upper bound is that you can't do more than the number of variables. So if B has x variables, then I of B, I tilde of B can't be more than x. Okay. So what's interesting about this is that Strawson showed, if you sort of reinterpret one of his results in our notation, showed that matrix mult tensors have really big I tilde. So like the matrix mult tensor MMM, which you'll remember, it has m squared x variables, m squared y variables, and m squared z variables. Its I tilde is as big as possible. It can monomial degenerate into lots of independent terms. And so if you have an algorithm using the galactic method, so you monomial degenerate from your tensor to a matrix mult tensor, you can compose it with Strawson's monomial degeneration and get a big monomial degeneration from your tensor to a huge independent tensor as well. And so if you want to show that the galactic method can't be used with a tensor to show omega is 2, you just have to show that I tilde of that tensor has to be less than the number of variables. So that's the main proof idea. And then the rest of our paper is like a bunch of sort of combinatorial gadgets for proving this type of thing for a lot of different tensors. So let me quickly give you just one example that'll actually be enough to prove the Coppersmith-Winograd lower bound. So one of the lemmas we prove is that if T is a tensor that can prove omega is 2 with the galactic method, Then there's a way to find a probability distribution on the terms of the tensor. So you assign a probability to each term, so they sum to 1, so it's a probability distribution. And for each fixed x variable, or fixed y variable, or fixed z variable, you assign 1 over k, like the same probability mass to each fixed variable, if there are k variables. So a probability distribution so that each variable is assigned the same probability mass. This sort of follows from the independent tensor notion, if you think about it a little bit. And actually, it's really, yes, I'll call this P of xi, is the sum of the probabilities assigned to xi. And it's actually really easy to see that the Coppersmith-Winograd tensor can't have such a probability distribution. I'm actually only going to use the last 2 terms of the tensor, okay? So if you look at this term here, it has the only occurrence of yq plus 1. And so since this tensor has q plus 2 variables, that means we have to assign it probability 1 in q plus 2. Similarly, this last term here is the only term that contains zq plus 1. So we also have to assign it probability 1 in q plus 2. And this is already a problem because both those terms have x0 as their x variable. So we've already assigned too much probability to x0. So the Coppersmith-Winograd tensor can't have one of these distributions, and so it can't prove omega equals 2. That's, yeah, modulo, lots of details. That's basically how the proof works. Okay, yeah, so just to conclude, I think like these limitation results might seem kind of sad, but I think they're actually nice in that they can help us narrow in on tensors that might be able to prove omega equals 2, like you want to sort of pattern ones that have the distribution and so on. And I think it would be exciting to prove more lower bounds or even more upper bounds. Yeah, so thanks. Yeah, so basically if you have a tensor of rank k and you monomial degenerate it to another tensor b, then that shows b has border rank at most k. Yeah, it's very related to border rank.
So Buck-Savage work, he always just proves monomial degeneration doesn't work, or does he prove also that any degeneration?
Yeah, I think he proves that any degeneration. To be honest, I don't actually understand his work very well, but I talked to Josh Gochow about it for a long time, and he says that it shows it for any degeneration. Yeah. Yeah.
Do your lower bounds get sort of quantitative lower bounds for anything?
Yes. So we mostly focused on just showing there was a constant bigger than 2, but the other day I worked out what it is, and I think the lower bound constant we get is 2.0003. So we do get a number. I think with a little bit more work, you could improve it to like 2.01 or something like. Like I think this is a pessimistic estimate of what the number is.